Does IPv6 scare you? Does it freak you out? Does it remind you of Freddy Krueger? If it does, have no fear. Hey guys, Nachkazi here, and in today's video, my primary objective is to conquer this beast. If terms like neighbor discovery, SLAC, duplicate address detection, solicited node multicast are fuzzy to you, no worries. By the time you're done watching this video, not only you'll know these terms, but then some. So what are we waiting for? Let's roll! Welcome to CCNA 200-301 course. Today I'm going to cover section 3 part 4, IP addressing and routing. Today is all about IPv6. We're going to do a deep dive. Here are the topics I plan on covering today. Number 1, fundamentals of IPv6. Number 2, IPv6 address types and scopes. Number 3, IPv6 neighbor discovery. Number 4, IPv6 address assignment. Number 5, IPv4 to IPv6 migration strategies. Number 6, IPv6 routing and subnetting. And finally, I'll wrap it up with an IPv6 lab. Let's roll. Fundamentals of IPv6. So why IPv6? Well, first of all, we have actually ran out of IPv4 addresses. The only IPv4 addresses that exist today are the ones that somebody else had purchased, either an ISP or a customer, and they no longer have a need for those IPs, and they willingly want to give those IPs up. Then we basically get them repurposed and get them reallocated to a different customer who actually has a business need. Plus, the IPv4 addresses were very poorly allocated to begin with. Like in the beginning of the internet age, if you will, a lot of big universities here in the US, for example, ended up procuring Class A and Class B style of public IPv4 address ranges, and that is absolutely ridiculous. Nobody should ever need a Class A or Class B style of IPv4 address space. And because of that, we had a really poor allocation of how the IPv4 addresses were assigned. Another element that is important to consider is things like network address translation, which I talked about in one of my videos, and RFC 1918 private IP addresses, which is basically a private IP address range you can use within your LAN, but you cannot route these IPs over your WAN. These two technologies, private IP addressing and NAT, are considered to hinder the innovation because everything in the networking stack has to be built around these two technologies. Instead of focusing on innovation, we're basically creating like a workaround, and that is an obstacle to coming up with creative ideas that can benefit us, that would allow us potentially to have end-to-end connectivity without having to NAT, for example. And if you think about it, I mean, we actually have a need for a larger address space. And why is that the case? Well, if you think about it, there's more people on planet Earth today than there were back in 1970s and 80s when the internet was being designed. And there are certainly a lot more devices online than there were back then. So, case in point, currently the world population is over 7.8 billion, and it's increasing by the day. So if you think about it, even if half of the world's population is using the internet, then IPv4, we know, if you watched any of my previous videos, you can only have roughly 4.3 billion IP addresses in IPv4. Well, if half the world's population is on the internet, right there, we're pretty much at capacity. But if you think about it, each human being actually has multiple devices. So if you accommodate for that, let's assume there's 3 billion people online, and all those 3 billion people have two devices that they use. They have a phone and they have a laptop or a desktop. So 2 times 3 is 6. That's 6 billion potential IP addresses that you may need for those devices to talk to each other. That's beyond the capacity of IPv4, hence the need for IPv6. And then think about devices. We have devices like IoT, Internet of Things, right? So we got IP cameras, and we got smart devices and smart meters and smart city that has all these different sensors that are placed throughout the city and all that stuff. You need a lot of devices now with IP addresses assigned to them so you can remotely manage them, configure them, have visibility into them, and capture the data that you need to be able to make intelligent decisions, which is part of the digital transformation that the world is going through today. That's another important reason for needing an address space that allows us to do that. And we also need a global reachability and flexibility, end to end. So for example, from my phone to your phone, we want to talk to each other without using NAT. Now, I understand that some security people think that NAT is a good technology because it allows us to hide our private IPs, but the only reason we have this view of the world today is because that's the only lens we have that we view the world from. But if you were to look at the world from a different lens, aka IPv6 lens, then we'll realize that we have the ability to be able to connect devices end-to-end without compromising security, because IPv6 comes with some standard security features built in. And speaking of features, here are some of the key features of IPv6. It's designed to be plug and play by nature, meaning you don't have to configure your network much. As soon as you plug in the devices and you enable IPv6, the devices just automatically start talking IPv6 to each other. The network header of IPv6 has been streamlined compared to the IPv4 header. There are no more broadcasts in IPv6. Really interesting. We'll talk about that. There are extension headers. That's a field within the IPv6 header that's been added that allows a lot of flexibility to IPv6, which means new extensions can be written in the future without having to rewrite the entire protocol. And finally, we have better security with IPsec support. These are only a subset of features. There's a whole plethora of additional features, but I just wanted to highlight some of the strongest features of IPv6. Now let's look at IPv6 from the OSI model perspective, and there's a very important point that I want to hit on for you to understand the role of IPv6. What we have is an application, for example, an email that I want to send from my machine. And that email will use TCP at layer 4 or the transport layer. At layer 3 or the network layer, it's going to have to use IP. At layer 2, it may use Ethernet. There might be another technology, but let's just assume it's Ethernet because that's the dominant technology in use today. And then at the physical layer, we'll have bits and bytes and all that, and electrical signals and photons. But the key here is that what we do when we go from IPv4 to IPv6 is that we just simply stop using IPv4 and we switch over to IPv6 at the network layer of the OSI model. So all we're doing is just changing the stack at the network layer, and the layers below IP and the layers above IP remain the same. And that's the beauty of having a reference model like OSI in a Lego block style, is because we can go ahead and add different components to different layers of the OSI model without having to rewrite the entire thing. And that's why it's such a powerful reference model and it has survived for so long, is because of its modular nature. Now let me give you a quick overview of IPv6. So the IPv6 address size is 128-bit. That is absolutely ridiculously gigantic, and we'll talk about it in a moment. It's defined in RFC 2460, as opposed to IPv4 address space of 32-bit. And what that means is we have 3.4 times 10 to the power of 38, or 340 undecillion addresses, or it could also be rewritten as 340 trillion. Now that is an absolutely insane amount of IP addresses. And to put things in perspective, let's quickly take a look at this chart right in front of you. So all the way up top, we got a million, then a billion, then a trillion, then a quadrillion, and we keep going down until we get to undecillion, okay? And we have how many of these undecillions? We have 340 of these bad boys, the undecillion. I mean, this is an absolute craziness. So the bottom line is, unless our scientists start assigning an IP address to every single human cell in our body, we shouldn't actually run out of IPv6 addresses for the foreseeable future, or at least for the next couple of generations. In IPv6, the address is divided into 8 groups of 4 hexadecimal characters each. So let me show you how an IPv6 address could be written. Now, as I mentioned earlier, IPv6 is one of those topics that absolutely instills a fear of God in people's heart, because it's so different. Hang in there with me. Throughout this video, I will keep explaining different components and how the structure of the IPv6 address works. So by the time you're done, you'll be very confident. And I encourage you to actually watch this video a couple of times for this topic to sink in, especially if you're brand new. But if you are already familiar with IPv6, then this video will absolutely solidify your knowledge in the realm of IPv6. So back to the address here, as I mentioned, it's 8 groups of 4 hexadecimal characters each. So each character here is a hexadecimal. So 4 is a hex, 0 is a hex, 0 is a hex, 1 is a hex. Then after the colon, all of these values are hexadecimal, all of these values are hexadecimal, and so on and so forth, all the way to the end. Each hex character is 4-bit, hence each quartet is 16-bit. Another element I want to bring to your attention to is this one block of IPs is called a quartet, as opposed to, if you remember, in IPv4, we had octets. So IPv4 had octets. Here in the IPv6 world, we have quartets. And each quartet is 16-bit because each hexadecimal character is 4 bits in binary, and 2 hex characters make up a byte, or 8 bits. So if this is 4 bits and if this is 4 bits, then if you were to combine them together, that's 8 bits, and 8 bits equal 1 byte. Now let's quickly look at the conversion chart. Here's a decimal, hexadecimal, and binary conversion chart. Now, technically, we don't need to worry about decimal when it comes to IPv6 addressing because everything is in hexadecimal. But as I mentioned, each hex value in IPv6 is composed of 4 binary values. Okay, so 0 would be 4 zeros. If you look at A, that's 1010. And Y is 41010. Well, if we map this back to handy dandy binary conversion charts, so 1, 2, 4, 8, these are different bit positions. Well, if we were to enable this bit, because this is A equals 10 from a decimal perspective, right? So that means this bit position is on, 4 is off, 2 is on, 1 is off. Well, when 8 plus 2 is on, that would be 1010. And that's exactly what we're seeing here. That's A. And when it's F, that's all ones. With this context in mind, you'll be able to understand IPv6 addressing in a much better way. So there are two rules to shorten the IPv6 address. Rule number one is eliminate group of consecutive zeros via double colon. So what does that mean? So if we look at this full IPv6 address that we looked at just a moment ago, 4001:0070, so on and so forth, the simplified version of this IP address could be written as this. So what that means is, you see what we're doing here is we're taking a chunk of these zeros, these three quartets, quartet number 3, quartet number 4, and quartet number 5. We're taking them and we're collapsing that into colon. So that's one of the ways this can be re-represented and rewritten in a more simplified format. Because remember, as human beings, machines can understand binary. They don't even worry about hex and all that. At the end of the day, machines only understand bits. As human beings, our understanding of the world is more limited because of our limited capacity. So we have to make sense of things, and for us to make sense, we can only understand a very small string of numbers. So because IPv6's address is ridiculously large, powers that be who designed IPv6, they came up with the strategy of compressing the IPv6 addressing in such a way that we can kind of minimize the address space so it's easier for us to look at and make sense of. Now, to continue building on this, rule number 2 is we can also drop the leading zeros. What that means is the simplest form of this IPv6 address that we just looked at. So initially, this is how we write the full address. Then we simplified it further. And if you look at this one, this is the simplest form. And what did we do here? We dropped these two zeros and we dropped this zero right here. You see they're missing. If you look below, right here, these two zeros in blue and this zero in blue is missing. And the reason it's missing is because it's totally allowed according to the rules of IPv6. Couple of additional things I want you to keep in mind. Successive fields of 0 can be represented as colon, but that can only happen once. Here's an example of an IPv6 address right here. And this can be rewritten as, you see what we did was we took the second quartet and we collapsed it in a single zero. We don't do double colon here. But you see, we took the 4th and the 5th octets and we collapsed them into double colons. In other words, according to the IPv6 rules, wherever we have the longest set of zeros combined together, we'll collapse that into double colons. And where we have a smaller set of zeros, we can just collapse them into a single zero. That's totally legal, totally allowed. Here's another IPv6 address we can look at. So FF01:000 all the way down to 1. Look at what we did. We took all of these quartets and we collapsed them into colon. See, now it's a lot easier. This is even easier than IPv4, for God's sakes. FF01:1. So I'm starting to like IPv6 already. Now let's take a look at this. So we took an address that's represented as all zeros and a 1 at the end. We took all these zeros and collapsed them into colon 1. Now this smokes IPv4 in simplification. I mean, it can't get any simpler than this. I mean, this is absolutely beautiful. And I mean, check this out. If you thought this was beautiful, I mean, here you might actually get tears in your eyes, okay? Here we have all zeros collapsed into colon. How beautiful is that? And by the way, this is how we represent a default route in IPv6. This is way simpler than 0.0.0.0 in IPv4. Remember that, guys? When we configure default route in IPv4, tell me if this doesn't smoke this 0.0.0.0. So you see, IPv6 can be simpler if you can look at it a little bit differently and understand the rules and regulations of IPv6. However, there are a couple of things you need to keep in mind to make sure you're not stepping into the illegal realm, meaning you're not doing anything that's not allowed. So for example, you can't have double colon twice. So you can't have an address that has colon here and colon again. You cannot do that because this confuses the system, okay? You may be able to do it when you're writing it on a piece of paper, but computers will never make that mistake. And this is against the rules of IPv6 addressing. So keep this in mind because this could be a beautiful exam question to get you to see if you really understand the rules of IPv6 addressing. Now let's quickly look at the difference between IPv4 and IPv6 header. Now to the left is an IPv4 header. It's 20 byte in length and it's composed of 14 fields. Okay, so if you were to count all these fields in this header, there are 14, trust me. Go ahead and count them. And if you look at the IPv6 header to the right, in contrast, it's double in length, it's 40 byte, but it's a lot more simplified. It's only 8 fields as opposed to 14 fields. So it's been really, really optimized. You have different fields like version that actually says it's version 6, traffic class is used for QoS, flows is used for the sequence of packets and to avoid packet reordering. Payload length is all about payload. Next header is the extension header that we talked about, which allows a lot of flexibility to IPv6. Hop count, basically TTL in IPv4 has been renamed to hop limit in IPv6 header. And then we have a 128-bit source address, and then we have a 128-bit destination address. And to the left, the legend here shows all the fields that have actually been removed or pulled from IPv6 to make the header more streamlined. Now let's shift our focus to IPv6 address types and scopes. This is the key topic. If you guys understand this, you'll pretty much understand everything there is to know about IPv6. In RFC 2373 section 2.4, IP addressing architecture is defined. And what it says is that we take the IPv6 address and we break it into different portions. And the leading bits define the specific type of an IPv6 address. So if you look at the table at the bottom of the screen here, you'll see how the RFC has carved out the entire IPv6 addressing architecture. So in the first column, you're seeing the allocation. In the second column, we see the prefix in binary. And then finally, in the third column, we see the hexadecimal value associated with those prefixes. So if you look at our allocation number 1, called Aggregatable Global Unicast Addresses, the prefix start with 001 in binary. And it's represented in hexadecimal as 2000. Now you right now might be extremely confused. What does that even mean? So let me do some whiteboarding to explain. If we were to look at the address, let's say 1A to C. This is the first quartet in the IPv6 address space. Each of these values here is a hexadecimal. Each of these digits is a hexadecimal digit. So if we were to zoom in to the 1 here, it's actually 4 bits. So these 4 bits could be, for an argument's sake, say it's all zeros, and then the second would also be all zeros, and then so on and so forth. The RFC says that regardless, the bits will always start with 001. That has actually been reserved. What we'll do afterwards is we'll then have all zeros all the way through. And where this range would end is, once again, the first 3 bits are always going to be reserved according to the RFC standard. So what we can do is we can almost draw an imaginary line here, and everything to the left of this line is reserved according to the RFC. But to the right of it, we could have all the ones in the first quartet. And if we did that, let's say if this is the start of the range, where we have all zeros here, and then the bottom here, if this is the end of the range, what we'll get is the value 2000 all the way up to 3FFF. Well, you might be asking, where does the value 2000 come from? Well, if you look at the first hexadecimal digit, because the RFC says it must be 2, That means if you look at these 4 digits here, and if you look at our binary conversion chart, 1, 2, 4, 8, that means the bit in the third position, the third most significant bit is actually on, all the other bits are off. That means that our address will start with 2000 because the first digit is 2 and then the rest of the digits are all zeros. And the highest value that we can get is 3FFF. And what that means is, once again, look at the bottom here, 2 plus 1 equals 3. And then if the rest of them are all ones in hexadecimal is F. So that's the total range of global unicast IPv6 addresses. Now, the second type of allocation you want to look at is link local unicast addresses. So the link local, the first 10 bits must always be in this sequence as we see. And when we convert them into hexadecimal, we get FE80. Well, next up is site local unicast addresses. And here's how the sequence is specified, and it should translate to FEC0. And finally, we have the multicast addresses. And what we see is the first 2 hex digits in the first quartet of the IPv6 address will always start with FF. Now that said, it's very important that you understand that the site local unicast addresses, that has been deprecated. We now have what are called unique unicast addresses or unique local addresses. And we'll talk about that in a moment. A new RFC came along and it basically invalidated this site local unicast addresses. It changed to something different, and we'll talk about it momentarily. Now, here's what I plan on doing next, guys. I'm gonna zoom into each of these allocations so you get to see how each of these components are specified according to the RFC standards. First, we'll look at IPv6 aggregatable global unicast address. Say that 3 more times. Number 1, it's the same as IPv4 public space. So if you want to look at it from an IPv4 perspective, you can think of the public range of IPv4 addresses, which means these addresses are internet routable. We talked about the prefix range. I did the binary math for you a little bit ago. So the entire range is in hex, begins with 2000 and goes all the way up to 3FFF. It can also be represented as 2000:/3. And the way this gets carved out by the service providers is, once again, the first 3 bits will always be 001, right? So that's the first 3 bits. The next 45 bits is the global routing prefix that's assigned to the ISPs, and that's the provider space. And then what we get here is the 16 bits at the site level, and this is something that's assigned to the customers. If you need a internet routable IPv6 address, you'll go to your ISP and request a block. Your ISP will give you a subnet, and then you can take that subnet and assign it to the rest of your organization. And if you want, you can also further subnet it, meaning you can further subdivide it into multiple additional networks if you would like, so you can accommodate your entire company. If you have 100 offices or maybe even 10,000 offices, or regardless of the number of offices, you can just take the appropriate block from your ISP and allocate the chunks accordingly. And the cool thing is, we'll talk about subnetting in this video, so just hang in there with me as we continue moving forward. And then the final piece is the last 64 bits are the host ID, and typically the last 64 bits are the interface ID, which basically is a combination of MAC address and some additional data that's attached to the MAC address, and we'll address that momentarily. Here's another way of looking at it. The registry prefix is assigned by IANA, which is the Internet Assigned Numbering Authority, and it's assigned to the Regional Internet Authority. So this could be for us, for example, ARIN, which stands for American Registry for Internet Numbers. And this could be the initial chunk. This is just an example. Then Aaron might assign a chunk, a /32 block. So the top block was /16. Then Aaron might assign, let's say, AT&T or Verizon or Comcast or whoever a /32. And then the ISP will take that chunk and allocate a /48 block to the customer. And then the customer can take that /48 block and assign /64 for individual links, for example. And this gives the customer the ability to play with 16 bits. 64 minus 48 is 16 bits. So the customer can play with these 16 bits to further subdivide or create subnets within their network and allocate chunks to different sites accordingly. Now let's look at IPv6 link local address. It's assigned automatically. As soon as the IPv6 host comes online, it just automatically gets a link local address. You have to do nothing. It's very similar to, if you guys remember how Windows would allocate 169.254 addresses. If you ever remember seeing one, you typically get this address when your machine is unable to contact a DHCP server. It will self-assign itself a 169.254 address. That's also called a PIPA, which stands for Automatic Private IP Addressing in Windows. Every IPv6 interface must have this address. So the previous address that we just finished talking about, the global Unicast address, that address is not a must. You don't have to have that address. You only need to have it if you're going to route traffic to the internet at an IPv6 level. But if you just need to communicate with other devices within your LAN or local area network, you can get away with just having link local addresses that are automatically assigned. And these addresses use Neighbor Discovery Protocol, or NDP, which replaces R in IPv6. And the link local addresses, according to the RFC standard, always begin with FE80::/10, which means the first bits are always in this sequence as you see in front of your screen, followed by 54 zeros. And there's something interesting in IPv6 called Modified EUI 64, and EUI stands for Extended Unique Identifier. And what that means is we take the last 64 bits in the IPv6 header, and we also look at the MAC address of the machine, and MAC address is 48-bit, and we manipulate those bits. To explain this better, let me quickly jump on CLI so you see what I'm talking about. So let's quickly take a look at the MAC address of our machine here, of our fast Ethernet interface. Let's do show interface fast Ethernet 0/0. You see what happens with the link local address is we look at our burned in address, which is our MAC address. By the way, the difference between the MAC address in parentheses with BIA in front of it, which stands for burned in address, and the MAC address to the left of it is that on a Cisco device, I'm on a Cisco router right now, I can go ahead and manually assign a MAC address, which is different than the manufacturer ID. But the ones that's assigned by the manufacturer is a unique address, and that's the one that's called burned-in address. Now, I may change the one to the left, but I cannot change the burned-in address. Okay, I just wanted to quickly specify that. Now, let me explain how Modify EUI 64 works. If we were to take this MAC address and do what it's suggesting us to do, which basically says we take the 48-bit MAC address and we insert FFFE in the middle of it, and then we change the 7th bit. Let me show you what that means. Let's do that together. First thing it says is we're gonna divide this into two different pieces. So there's CC01B2. That's one portion of it. That's the first 24 bits of this MAC address. And then we'll do 65.0000. So once again, this is the first 24 bits. And this is the last 24 bits of our MAC address, right? Because MAC address is a 48-bit address. And see what it says? We have to insert FFFE in the middle. So we do FFFE in the middle. But then it also says one more other thing. It says we also have to flip or invert the 7th most significant bit. And this bit is called U/L. It stands for universal or local bit. When it's set to universal or U, that's the manufacturer ID. Okay, so that's the one set by manufacturer. If it's L means it was defined by the administrator. So what we want to do is, because we are modifying this bit, this tells the router that this bit has been manipulated by an administrator. The 7th bit here means, remember, this is the hexadecimal address, right? So each hex is 4 bits. So we'll take CC and zoom in. How is C represented in binary? Well, remember the handy dandy chart, 1, 2, 4, 8. We're going to look at that, and then 1, 2, 4, 8. We can do that. And then find out this C position. But before we do that, we need to even figure out what C means from a decimal perspective. C is 12 in decimal. Well, we're going to have to come up with number 12 here. So if 8 is on, and 4 is on, and 2 and 1 are off, that gives us a value of C. Now this says we have to flip the 7th bit, but let's go ahead and finish this out first. 1100. Now, if you look at the bits here, starting from left to right, this is bit number 1, bit number 2, bit number 3, bit number 4, 5, 6, 7. It says to flip it. That means if it's 0, we're going to set it to 1. Well, when we do that, what happens to this C? This C now becomes 8 plus 4 is 12. So that's C. Plus 2 makes it 14. 14 will make it E. So we'll have to now switch this to E. So it's going to become CE01. Now let's see what the router does when I go ahead and enable IPv6 on the interface. So I'll do configure terminal, and I'll go to interface fast Ethernet 0/0, and I'll say IPv6 enable. All I have to do is just type in this command to enable IPv6 on this interface. That's it. And you'll see what happens. When I do show IPv6 interface, you'll see that we only have one interface that's running IPv6. Now, currently it's administratively down because we haven't enabled it yet. But you see it says IPv6 is enabled. Link. This is a link local address, and it's set to FE80 and then CE01 B2FFFE65. So now let's compare this value, which was calculated by the modified EU64, and see if this matches the math that I did earlier. And let's take a look. And sure enough, you see CE01 B2FF FE65 0000, and that's it. So that is really cool. Here's another example of applying modified EUI64 to a MAC address. So it becomes this address right here based on all the steps that we went through. If you were to apply those steps here, you can pause the video and actually do this. I would suggest you do this, and you'll come up with this value that will reinforce some learning. Now you might be thinking at this point, why did we have to do this? Well, the reason we did it is because we want to make sure that our last 64 bits of our IPv6 address will always be unique, because we don't want to run into duplicate IP address situation, right? So when we take our MAC address, which is supposed to be universally unique, and then we add this modified EUI64 math to it, it's supposed to make it even more unique. And there should never be, at least theoretically, a case where you should find 2 IPv6 devices on your network with the same address. If you do, then there are additional mechanisms that actually protect against that, and we'll talk about that in a moment. But theoretically, you should never have that problem. Now let's talk about IPv6 unique local addresses. These are analogous to IPv4 private IP addresses. So you guys remember 10.0.0.0/8 and 172.16.0.0/12 and 192.168.0.0/16. That's exactly what the unique local addresses are for, which means they're not routable on the internet, and they're not registered with any numbering authority. They're only valid on your local LAN. And initially, IANA reserved a prefix that began with FC00::/7, but then another RFC came along a couple of years later, RFC 4193, that changed things a little bit, and it says that the 8th bit is set to 1. So in practice today, what you should see in real world is a unique local address that begins with FD00::8. But you should also know this address for exam purposes. And here's how it looks like. When we say FD, like these are the first two hex digits, that's the first 8 bits that, they're reserved. That's how it looks like. The rest of the 40 bits, that's global ID for our network. What we can do then is we can play with 16 bits to do subnetting. And finally, remember, we always want the last 64 bits in IPv6 to be associated with the interface ID. In other words, if I were to draw a line in the middle here, the bits to the left would actually be what you would call network bits. The bits to the right are host bits. Once again, very similar to IPv4 from an overall logic perspective. So if you guys go and watch my IPv4 addressing video, you guys will start to understand the fundamentals of subnetting. I highly recommend that you understand the IPv4 subnetting first before we get into the IPv6 subnetting, because it's going to be a lot easier. Now here's a quick recap of IPv6 address types and scopes. First, we have a link local address. That's a must-have address. And the use case for this one is it's local to the link between two IPv6 endpoints. We have unique local address next. That's optional. It's organization-wide address space, and it's analogous to IPv4 addresses. We also talked about global unicast address. This is also optional. The use case for this one is internet routable address space, and this is analogous to the public IPv4 addresses. And this is how the scope looks like. So if you were to visualize the scope, the link local addresses have a very narrow scope. They're only good on a link. Then the unique local address scope is organization-wide. So this is your entire company. And then the global scope is the internet routable address space. Now let's quickly talk about IPv6 multicast address. This is the last type of addressing we'll discuss according to RFC 2373. It's analogous to IPv4 Class D range. So if you guys remember 224.0.0 through 239.255.255.255, that's what IPv6 multicast address space is analogous to. First bits, according to the RFC standard, are always set to FF and also represented as FF00::/8. Now, if you were to look at it from the addressing space perspective, these two hex digits, FF, which in binary are all ones, they are reserved. And then the bits right next to it, you could have a flag here. Typically, you'll see that as a 0, which means permanent. Unless it has 1 in front of it, that means it's temporary. And then the last hex digit in that quartet would be the scope. And you'll see things like 02, for example. You'll see that a lot. As a matter of fact, you'll see FF02 a lot. That 2 means it's a link local scope. Okay, so something to keep in mind. Now, here is a multicast address table to show you how it all connects to help crystallize IPv6 multicast groups. All host address in IPv6 multicast is FF02::1. It's analogous to 224.0.0.1 or all host broadcast, which is all 255s. That means when you send anything to this destination, all hosts will get it. In contrast to if you send something to FF02::2, that's equivalent to 224.0.0.2. That's all routers, not all hosts. Only all the IPv6 routers will get packets in this multicast group. Another type of address that's important for you to understand is solicited node multicast. And that is FF02::1:FF00 192.168.0.0.0/104. This is what replaces ARP in IPv6. So remember ARP in IPv4? What's the purpose of ARP in IPv4? The whole idea is we already have an IP address. We need to determine the MAC of the other machine, the destination machine. In this case, in IPv6, solicited node address is used to find the MAC address of the destination host. And let's go back to the CLI so I can show you a couple of things that we just discussed. So remember we were looking at show IPv6 interface earlier. Look at the joined groups. These are the multicast groups. So FF02::1, what is that? Well, we just looked at it. FF02::1 is all hosts. So that's what it is. Okay. And then the one underneath it is FF02::1:FF65:0. And you see this solicited node address here at the bottom, FF02::1:FF. That's what's being represented here. Now let's quickly shift our attention to IPv6 neighbor discovery. In IPv6, what we have is a neighbor discovery protocol, or NDP. It's defined in RFC 4861, and it's part of ICMP version 6. So if you guys recall, an ICMP is Internet Controlled Message Protocol. It also exists in IPv4, so every time we ping or we trace route in IPv4, we're actually using ICMP. In IPv6, it was rewritten as ICMP version 6 to accommodate the IPv6 header. And what ICMP is a suite of diagnostic tools that we can use to see whether or not the remote device is alive, whether or not we can get to it, how many hops exist between us and the end device. So it's a diagnostic type of tool used in networking. And neighbor discovery's main function is to discover and track other IPv6 hosts connected on interfaces. Very similar to ARP in IPv4, neighbor discovery relies on ICMP version 6 messages and solicited node multicast addresses for its core functions. Here are some of the key functions of neighbor discovery that are very important to know, and this is what makes the entire IPv6 plug and play. The first function of NDP, or neighbor discovery, is neighbor MAC discovery. We have to find the MAC address of our neighbor. The second thing is we have to find who the local router is. The third thing is SLAC, or stateless address auto configuration, meaning it's a fancy term for saying we need to be able to automatically assign an IP address to ourselves. And finally, we have this idea of DAD, or duplicate address detection, or DAD. Duplicate address detection protects us from the devices that auto-configure themselves somehow using a duplicate address. They kind of go hand in hand. And one of the things that I can show you is, let me jump back to the CLI again one more time. You see, when I typed in the command IPv6 enable on my router, I didn't specify an IPv6 address, yet my device automatically assigned itself a link local address. That's what's called SLAC, or stateless address auto configuration. Okay, it's stateless, meaning that there is no state to it. It's just every time a device comes online, it just automatically assigns itself an IPv6 address. And the funny thing is, the interface is administratively down right now, yet it still assigned itself an IPv6 address. While we're at it, we'll just go ahead and enable this interface and then run the command again, do show IPv6 interface. Now the interface is up. And one more thing we should do is type in the command IPv6 Unicast routing. And that is a global configuration mode command, and that is an important command to make sure that IPv6 routing is enabled on your router. Thanks for sticking around. By the way, there's a lot more to this video than what you have seen. In order to watch the entire video, you're gonna have to be a little patient because I'm working on designing an entire CCNA course. I'm gonna do an official launch in the next couple of months, but until then, I'm gonna keep putting little nuggets of the CCNA exam out there on my YouTube channel until the course is ready to be published. Hope you enjoyed today's video. If you did, give me a thumbs up, hit subscribe, and I'll see you in the next video.